that we finished with proving the KKT conditions. That's what I remember. Is that true? Good. So I want to summarize last lecture by first stating again the KKT conditions. And then I want to show some interesting properties of them again. So I just want to recall what we have proven and what we will use a lot in optimization from now on. And that is if you have an optimization problem, so we have this problem minimizing a function f of x subject to some equality constraints and some inequality constraints. So that is our NLP. And what we have proven is that if you have an optimal point of this NLP, then there exist some multipliers so that the triple x star, lambda star, and mu star satisfies the KKT conditions. Yeah? So the theorem was if something is a local minimizer, then there exists lambda and mu, so that these three things together satisfy the KKT conditions. Yeah? So I maybe phrase the sentence: if x star is a local minimizer, then exist lambda star and mu star, so that this triple satisfies what we call the KKT condition. KKT conditions. And these KKT conditions are the thing that we derived last time, and they were actually given by the gradient of lambda with respect to x at these points being 0. So that was the most crucial thing. The equalities, of course, being satisfied. That was the trivial part, because feasibility should, of course, be given. Also the inequalities, positive. We also had this. But then there were two more conditions on the multipliers for the inequalities, namely that the mu star should be positive and that the mu star for each index multiplied with the corresponding index of the h should be equal to 0 for I from 1 up to q. Yeah, so that was the KKT conditions that we have proven. Do you remember them? Yeah. And they are necessary for optimality. So they are first order necessary conditions. So FONC. And I will not go into this proof, but I want to recall that we used some deep result here that's called Farkas lemma, and that this lemma made it possible to introduce these multipliers. Yeah? And in essence, these conditions are nothing else than somehow saying that for all feasible directions, only can lead uphill. Yeah, so this statement, this one here in particular, was basically equivalent to saying that for all p that are feasible directions, the gradient, the product, so roughly speaking, it was for all p in the tangent cone. Yeah, we have that p times nabla f of x star is going uphill. So that's basically what they mean, plus some extra. So we had to assume LICQ, that was the first step, yeah, in order to make this equal to the linearized feasible cone. When we have the linearized feasible cone, then this is can be replaced. But then the transition to this condition was a bit more involved. But it's of course much more computational, because now if someone gives you these 3 points, you can test if it satisfies the KKT conditions. And this way allows you actually also to to search for points that satisfy these things. And that's what all algorithms for optimization do. They try to find points that satisfy KKT conditions. And if you have found a point which satisfies KKT conditions, it doesn't mean that it's an optimizer, of course, but it's already a very hot candidate. And what is now really nice and beautiful is that if you have a convex problem, then you know already that it is even an optimizer. So for convex problems, the KKT conditions are necessary and sufficient. And this is something I still want to prove with you, because it's important and interesting. And we can prove it with relatively simple means, so I think it's worth to look at it. About the order of chapters, I think we are now in chapter 13, yes. Right? Should be 13. And maybe section 3, sorry. This is, I think, where we should be. So let's specify this thing for convex problems. And look at the KKT conditions again. And so there is a theorem, which I call theorem 13.6. So you assume that this NLP is convex. And now there is a strange condition, and we also assume that at the optimal point it satisfies LICQ. Yeah? And that at X star LICQ holds. So we have already a point, a candidate point, which is satisfying LICQ, because then there are two conditions which are equivalent. So X star is a global minimizer, and that is equivalent to the KKT condition hold. So there exist lambda star and mu star so that KKT holds. And these things together is what I call KKT. So maybe I should first say that this direction we have proven already. That's actually the same for convex or non-convex. So if X is a global minimizer, then it's also a local minimizer, and then this must hold. That's a necessary direction. But so for the sufficient conditions, we need to prove the other direction. So if these things, if they exist, and there exists some triple X star, lambda star, mu star that satisfies these conditions, and LICQ holds, then we should prove that X star is a global minimizer. And this is something we can do now, using only the tools that we had already before. And we only prove this direction. Yeah, so that's a sufficient condition. That's what we need to prove. Let us start this proof, and I just want to recall. So we start with a point that satisfies the KKT condition. So we have given these X star, lambda star, mu star with KKT. And what we want to prove is that there is that f of X star is the best possible feasible point. Yeah. Prove that f of X star is minimal. So the interesting first thing is that because these two conditions are part of the KKT conditions, X star is feasible. Yeah? X star is feasible, so in that sense we have already a feasible point. Yeah? And you also, actually maybe I should first say, what we want to show is that f of X star is equal to what we call P star, and P star was actually the minimum of f of X over all X, subject to g of X equals 0 and h of X bigger than 0. So this is the minimal value. Yeah, that's the language that we used in duality. So f x star is feasible, so that's already clear, so that's easy. And now we can go to define the Lagrangian function. So if we do this thing, I will look at this function. I will use the right multipliers, but I keep x free. And then I write this function, what was it, the Lagrangian? It will be f of x minus the sum of lambda star I g I x minus the sum of mu I star h I x. Right, so this is, and the sum is over all equalities and all inequalities. So this would be a function, and the interesting thing is now that we go on to think about properties of this function. So what properties does this function have? For a convex problem, yeah, so I want to show that this function is a convex function. This is convex also. Yeah. So that's what I want to show. And why is it convex? It's the sum of f, which is a convex function. These things are linear functions or affine functions, because otherwise the whole NLP is not convex. So maybe I should recall NLP is convex. What does it mean? It means f is convex, g is affine, and h minus hi is convex. You remember that? Yeah, because the negative, these functions h, they need to be concave functions basically. So minus h must be a convex function. And so now it is a sum of a convex function, f, affine functions with arbitrary sign, which are convex by definition. And here we have multipliers mu I, but mu I are positive or zero, so they are non-negative. And they are multiplied with minus h, which are convex functions. So it's again a sum of convex functions. So it's basically a sum of convex functions as a sum of convex functions. So in that sense we are happy here. And because it's a convex function, we know how to minimize it in the unconstrained case. Yeah, so we know that actually there is a sufficient optimality condition here, and we know that actually nabla x of this function at x star, lambda star, mu star is equal to 0. So we have found a point where the gradient of this function is 0, and it's a convex function. I should say it's convex in x, right? So I regard it only as a variable of x here. It would not be convex in lambda and mu, of course. It's a convex function of x. And we have a point where the gradient is 0. That means that x star, lambda of x star, lambda star, and mu star is equal to the minimum over all x in Rn of this function. It's just unconstrained optimality theory that we have had before. Yeah, so we know that this function is minimal here. So now, what is this? This is actually the dual function, the Lagrange dual function that we call Q, I think, at some point in this lecture, of lambda star and mu star. Do you remember the Lagrange dual function? That was this object is actually the Lagrange dual function, and because we fixed lambda star and mu star, this is it. And so you remember there was something that said weak duality, yeah? And you remember I recall actually a result that we had that was called weak duality, which we had proven actually. And that said that there is a value d star, which is actually the maximum over all lambda and mu of this function q, subject to mu being positive. And that this value d star is actually smaller than p star. P star being the primal optimal value and d star the dual optimal value. Okay, so that was a result we have proven and on which we can build now. And the interesting thing is that here we have this function q is evaluated at some point, lambda star and mu star. We know that the mu star are actually positive. So it's a feasible point for this problem. So what we know is that this thing here is smaller than d star, yeah, because of weak duality. So this is like a thing we can recall. But we know already from this whole thing that lambda, so the Lagrangian of x star, lambda star, mu star, which is the dual function evaluated at some point, lambda star and mu star, which might be the optimal one, but might also not be the optimal one. I call it star, but it's not sure that it's the maximizer of this problem, but because d star is the maximum of all possibilities, this as one entry of q must be smaller than d star. Yeah, so we have already this inequality, and then of course we also have the inequality that it's smaller than p star. So we know already that the Lagrangian function evaluated at x star, lambda star, mu star is smaller than the optimal value. That's a good thing because we want to be small. Now we have basically proven it already, because what is this thing, lambda of x star, lambda star, mu star, is actually f of x star plus minus, the sum of lambda star I g I x star minus the sum of mu I star h I x star. And what we see is, because of the KKT conditions, the g's must be 0 because they are feasible. So this will be anyway equal to 0. And here we have these products. So this must be 0 as well. So it is actually equal to f of x star. And so we know that what we know now is that f of x star is smaller than p star. And it is feasible. P star was the minimum of all feasible points. So that means that and x star is feasible. And these two things together, they say that f of x star is equal to p star. And on the way of it, we did not only prove that the x star is an globally optimal point, right? So that's what we have, that we wanted to prove. But on the way, we actually have also proved that the d star is equal to the p star, because basically what we got is here. I mean, we also have p star is smaller than d star is smaller than p star, which is equivalent to d star being equal to p star. So we have also proven that the dual and the primal problem have the same value here. So that is actually strong duality. That was the thing that we didn't prove before. But now we proved it. For this another special assumption that we have LICQ at the point. Because only then the KKT conditions could be applicable and so on. I should note, and this is the thing that I want to add, is that in convex optimization people very often use other constraint qualifications than LICQ. So instead of LICQ, other constraint qualifications are possible and usually actually used, and one of them is called the Slater condition. And I think we mentioned that condition before. The Slater condition says that there exists one feasible point which is in the interior of the feasible set. So which is not at the boundary. It's a slightly different phrase for constraint qualification. But for convex optimization, that is nice and actually a bit different, because what we did here say is we assume that the NLP is convex and at some point X star LICQ holds. So we needed the point actually in order to define our condition. If you say Slater's condition would be different in the sense that you say I have an NLP and it satisfies Slater's condition because there exists some feasible point in the interior, then any point X star is a global minimizer if and only if the KKT conditions hold. So in that sense, the statement can be a bit nicer phrased. But this way is, I think, satisfying and enough, and it's allowing us to prove with the little tools that we have at the moment everything that we want, namely that for a convex NLP, the global minimizer is exactly characterized by the KKT conditions. So the KKT conditions are necessary and sufficient for optimality. And that's it for today. What we will do next Tuesday is second order constraint, sufficient and necessary conditions. And then we go already into algorithms for inequality constraint optimization. But that's for it. Thank you very much and have a nice weekend.